All right, everyone. So this is chapter 7, which is in a way still continuing some of the application of Newton's laws of motion. So this chapter kind of specifically covers Newton's third law, where we talked about the Newton's third law being those action-reaction forces. That means when you have two interacting objects together, exerting force on one another. So for example, in this image, right, you have a hammer and a nail. Basically, during the strike, they are technically interacting with one another, and the force that hammer exerts on the nail, actually exactly the same force that nail exerts on the hammer. So that's why sometimes when you hit it, right, there's a little bit of recoil because the nail also, exerts force on the hammer. Anyway, so that's kind of like what we're going to be talking about. So you can see, right, when a hammer hits a nail, it exerts a forward force on the nail, and you can see, right, so this is the force that hammer exerts on the nail, but exactly same time the nail exerts force on the hammer in the opposite direction. So that's why you can say that when object 1 exerts force on object 2, at the same time object 2 exerts force on object 1, where the magnitude of the force is exactly the same, but they're in opposite directions. So that's why, what we're going to do here, we're going to look at some of the applications of this particular law, and there are plenty of applications, and we're going to see that some applications that you probably didn't even think of. So for example, you have a bat and a ball when they're interacting with each other, right? So the baseball player hits the ball with the bat. Well, that's an application of Newton's third law. Okay, so you hit the ball with a force in that direction, and well, technically the ball hits the bat in the opposite direction. So that's why there's again a little bit of recoil. So you can see, right, when you pull someone with a rope in a tug of war, the person pulls back at you. When your chair pushes up on you, the normal force, you push down on the chair. So that's why you can see that there's a force that you exert on the chair, right? It's basically technically equivalent to your weight, but you still have a force acting on it. So all forces come in pairs. Every force in the universe has a pair, and we call that action-reaction pairs. Okay, so these forces occur exactly at the same time, and you can basically say that those are the forces that acting on two different objects. You have object 1 and object 2 interacting and exerting force on one another. That means, when you're pushing the wall, you exert force on the wall, and when the wall basically at the same time pushes back on you, that's the force acting on you from the wall. So that means there are two different forces. All right. So then a lot of times when we have an example like this, where you have two blocks sitting next to one another, then at the, let's say, where you have this contact, right? This contact area between those two, right? There's a force between them because they are physically touching each other, right? Pushing on each other at that surface. So there's a force that box or the crate B exerts on A, and then the force that crate A exerts on B. And then what you have here is you have action-reaction forces. Okay, it means those are the two forces that only happens if they're physically, in contact. If you have box A sitting here and box B sitting there, those forces, non-existent, right? Because they're not physically touching each other. So the requirement is that they are interacting. They're interacting with, in physical contact at that surface. All right, same thing you can think of, like, let's say for the long range forces, right? So we talked about their contact forces, like push or pull, and then the long range forces like gravitational force, electric force, magnetic force, that also is action reaction. So you can see that, for example, you have Earth and the moon, and Earth exerts force on the moon. So this is the force toward Earth. Well, same way, moon exerts force on Earth. So now, because Earth is bigger, the effect is more visible on the moon. The moon is moving around like this, which seems like around Earth, right? In a circular orbit, but seems like Earth is, unaffected by that, but it's actually not true. Okay, the tides, for example, is due to the ocean tides, right? Is due to the gravitational force from the moon, right? The oceans basically rise, so you have a high tides, low tides, right? All of those things because of the effect of the moon, the gravitational pull of the moon. Later on, we will learn that technically the moon doesn't go around Earth. What we have here, if you, let's say, draw a line between the center of the moon to the center of Earth, then both of those, Earth and the moon, go around each other because of that force. They go around not each other, so they go around what we call the center of mass of the system. It's just that center of mass happened to be somewhere right there. Okay, so that's why the moon goes around that center of mass. But since that center of mass, a distance from, Earth, and then this is distance from the moon, right, to the center of mass, because it's much, the distance here is less than the radius of Earth, then it seems like the moon actually going around Earth, but in reality, it goes around that center of mass. Same thing, Earth, kind of like a wobbles around that. Same thing with any two celestial objects. All right, so this is something we'll learn in the later chapters. Okay, so you can see that in chapter 5 and 6, we considered forces acting on a single object. So this is basically Newton's first law and the second law. That means we had some object of interest, a box, a crate, or car, or person, whatever it is, right? And we would look at all the forces acting on that object. Then we would calculate the net force, and then the net force can tell us what happens to the object. Is it gonna, is it gonna be in equilibrium? Is it gonna accelerate? In which direction will it accelerate, and so on and so forth. That means we had one object of interest and all the forces were acting on this object alone. Now, one thing we can say now is there's also forces that this object A exerts on everything. That means, for example, there's if this is a agent 1, then there's an equal amount of force that A exerts on this agent 1 in opposite direction. This is agent 3, there's a force acting on agent 3 from A exerting on 3. This is agent 2, there's a force that A exerts on agent 2. All of those forces acting on those agents, but Newton's first and second law, we don't care about those forces. We don't care about the forces that A exerts on its environment or agents. All we care about forces acting on A. So that's why we didn't really talk about any of this stuff. But now we are going to be looking at that. We are going to be looking at the forces that object A exerts on environment and other things. So that's why we will be, we have an entire chapter on looking at that, the interaction of A with each separate agent. Okay, so you can write in this chapter we extend the particle model that we've been using to include 2 or more objects that interact. Okay, so the figure shows 3 objects interacting via action-reaction pairs of forces. That means, for example, you have object A and object B. They exert force on one another. And each line, right? Each line, you can write each line represents an interaction and an action-reaction pair of forces. That means A and B basically have 2 forces, 2 types of interaction on one another. C interacts with one action-reaction pair with A, C interacts with another action-reaction with B, right? So that's kind of what we have. You can write A and B can have more than one interaction. All right, so the forces can be, given labels such as FA on B or FB on A. So generally, this on I don't really use. So let's say I would just put FA on B, like AB together, which means A on B. And let's say BA means B on A. Just a little bit shorter to write it like that. But, try to understand my notation here. Okay. So this will be this guy over here. This will be that guy over there. So AB means A on B, BA, B on A. All right, so let's look at then a little bit, greater detail here. For example, let's say object A is the hammer, object B is the nail, and object C, the earth. All right, so the earth interacts with both the hammer and the nail through the gravitational force. So that's why, so let's say this is earth, so it exerts gravitational force on both of those. But at the same time, both of those objects exert force on earth with the same force, opposite direction. But obviously you don't see any effect on Earth due to the objects around it because the insignificant of the mass of those objects. Earth is, insanely, large compared to those objects. So the effect is very, very small. But let's see what we have. So you have practically the Earth remains at rest while the hammer and the nail moves because of that, right? Because, let's say the very small effect that object A and B have on Earth. So we're going to define the system. Okay, so our system is going to be defined as those objects whose motion we want to analyze. So define the environment as the object external to the system. Okay, now the question will be, for example, what two objects we want to, or what two objects motion we want to analyze. Do we care about Earth in this case? Well, not really. So then what we will do here is we will take the system to include a hammer and a nail because we want to look at the interaction between them. But we know that both of them have also Earth acting on them. So then this is known as interaction diagram. Okay, so where we take the system where we have A and B are hammer and a nail in part of my system, and C, which is Earth, then the environment. Then any force inside my system are internal, and any force outside of my system are external. Okay, so then that's important thing to know. So let's say that interaction are represented by lines connecting the objects, which are those red lines, right? And interaction with object in the environment are called external forces. All right, so let's look at then an example here. So how do you paddle a canoe in forward direction? And we're going to explain this using a free body diagram and interaction diagram. All right, so here's three different views of this problem. So here's a sketch on the left side. So the sketch basically shows that, a person inside the canoe and then with the paddle, right? And then basically how do you paddle a canoe if you want to go to forward direction? Okay, now what we have here is basically this. So we have, we identify all the, let's say agents, right? Actors in our let's say diagram in our problem. So there's water. So W is for water. Then PC is paddle canoe. E is entire Earth. S is then the surface. Okay. So then what we have here is we know that paddle canoe, right, basically interacts with water. Then there's also a surface, okay, and entire Earth. So let's say then what I have here is this. The surface basically interacts with water, right? And entire Earth interacts with water and paddle canoe and the surface, exerts gravitational force on them. And obviously then what we have here is the water and paddle and canoe exert, action reaction forces on one another. Okay. So now the way it works here is basically you push the water to the left, right? So basically pushing the water to the left, exerting force on the water. So for example, if you're looking at the free body diagram, right? So this is just the water. So what you have here is you have a normal force from paddle canoe on water down because it basically pushes down, right? And let's say then there's a paddle canoe acting, exerting force, which is to the left. So there's also gravity and things like that, but these are, kind of like, let's say inside my system, for example. We are trying to see in terms of how the water and paddle canoe, which is then part of my system, interact with one another. So free body diagram, because technically what we have is that in order for the paddle canoe to move forward, it has to interact with water. Okay, you push the water back, water then pushes canoe forward with the same force, kind of like that. So as you push the water to the left with the paddle, water then pushes you forward. Also, we exert a normal force, because there's a contact, right? Normal force with water, and the water exerts normal force on the canoe. Okay, so those are then, two interacting forces. So that's why there are two lines over there. So two interacting lines. So there's one and there's two because of those, those two are paired together. Those two are paired together and these two are paired together, right? So remember, the way you would identify the forces, interacting forces, always in the opposite direction. You can't have, a pair, one is horizontal, one is vertical. It doesn't work like that. Either two vertical, two horizontal, or, two such that there are, exactly opposite directions. All right, so one of the important, application and useful, obviously, application of the Newton's third law is, our ability to use ground to be able to walk or run. We call it propulsion. So let's say, how are we able to walk? Well, you can see, right, the way we walk, right, is we actually push the floor or the ground just like we would with the paddle, right? You push it backwards, so you can see, right, we push it back, and then the floor then or the surface propels you forward. So there's this action reaction forces. Okay, so that's why, for example, you can't walk on ice, or it's going to be very difficult, right? Because there's no friction. What propels you forward is the friction, static friction. So that's why we can't walk on ice, we can't drive on ice, because driving, right, or walking is basically pushing the ground in opposite direction, such that, assuming that there's a friction, and friction then propels you forward. So the static friction is our friend if you want to walk or, run and things like that. So that's why it's difficult to walk on ice, difficult to walk on sand, right? Because of the, friction or, negligible, amount of friction. Okay. Again, static friction is what propels you forward. So those are the three different applications of that, a propulsion. So the person pushes backward against the earth, or like a surface, right? The earth pushes forward to the person, static friction. A car pushes backward against the earth pushes forward on the car, again, static friction. The rockets, what happens here is that the rocket basically pushes the hot gas backward, basically down toward earth, and then those gases, right, basically push the rocket upward. That's how it operates. It's just basically dumping all the fuel down, right, basically pushing the gases down, and, well, the gas pushes the rocket up. So that's why it needs that, let's say all the fuel, right, all the gases enough so that it can propel it and escape Earth's gravity. All right, so again, Newton's third law, every force occurs as in one member of an action-reaction pair of forces. The two members of an action-reaction pair act on two different objects, as I mentioned. The two members of action-reaction pair are equal in magnitude, but opposite in direction. All right, so that's why we can say for every action, there is an equal but opposite reaction. So that's basically, exactly satisfy the Newton's third law conditions. All right, so let's look at one more example here. So the hand in the figure is pushing on the back of the block A. Well, there you go. So it's easy to see if there's actually a picture. So you have two blocks, A and B, and they're connected by a rope. And then the hand is basically pushing on the block A. Block A and B, where the mass of B is greater than mass of A, are connected by a massless string and slide on a frictionless surface. Is the force on the string on B larger than, smaller than, or equal to the force of the hand on A? So we want to kind of find that. Well, think like this. So one of the things we're going to be learning in a little bit, so this is kind of like actually a little bit jumping ahead. But one of the things we're going to be learning in a little bit is that we will be assuming that this is very important information. It's a massless string. Because if it's a massless string, that the tension from the string acting on block B, and then the tension from the string acting on block A, they are equal to one another. They're equal to one another. Okay, because it's one rope, the tension is the same everywhere on the same rope, on one rope. That means the tension is same, everywhere on that rope, which makes it important, information. Because if you're talking about, free body diagram for A, see the A is actually the only one being pushed by the hand. So this is the force of a hand on A. But then the tension acting in the opposite direction. But let's say since there's a, like, let's say frictionless surface, the system actually accelerates to the right. Well, if it accelerates to the right, that means the net force in the x direction equals F of h minus, let's say, tension. This is equal to the mass of A times acceleration. Okay. And what I have here is box, let's say the block B, right, has only one force acting on it, and then that's basically tension from the string. Now, since this tension is the same as the other one tension, right, acting on A, and there is acceleration on block A, and acceleration can only happen if F of h is greater than tension, means then the force acting on this force of hand, right, acting on A is greater than tension force acting on B. Okay, that means conclusion is that FH is greater than tension, because you can think of it like this: when you push with the hand force the block A, you technically have to push block A plus block B. So you have to push harder, where the tension acting on block B only has to be strong enough to push, or pull block B. Okay, that means the force from the hand is stronger than, let's say, the tension acting on block B. All right, so here's another one. Okay, so here's another one. And you basically, in this chapter, we're going to be looking at a lot of this type of problems where you have two blocks, connected. So these are two interacting systems, right? A and B together, connected by some kind of rope. Sometimes rope can go over a pulley and things like that. But the idea here is that you have two objects that are interacting with one another through some kind of rope. Because if there's no rope, right? So let's say in the previous example, right? Because, right, if there's no rope, if you're pushing A is just going to accelerate, B is just going to be sitting there. But because they're connected by a rope, whatever happens to A technically happens exactly to the, B. Acceleration of A and acceleration of B are actually equal to one another. Okay, we call this acceleration constraint. All right, so we have block A is heavier than block B and is sliding down the incline. All right, so sliding down the incline. All surfaces have friction. Okay, so the rope is massless and the massless pulley turns on frictionless bearings. Okay, the rope and pulley are among the interacting objects, but you'll have to decide if they're part of the system. So we're going to draw the interaction diagram, identify the system on your interaction diagram, then draw a free body diagram for each object in the system, and use dashed lines to connect the members of an action-reaction pair. Okay. All right, so what we have here is basically two blocks connected by a rope. Also, they're sitting on top of each other. Okay, so we have a gravity, right, acting on both of them. So let's say that's one of the forces, but obviously gravity technically always going to be sort of like environmental force in this case. So the two things that are interacting with one another directly that we want to consider, right, are basically those two, right, which is B and A. So we make a diagram, interacting diagram, where I can say, all right, so here's A and here's B. Okay, and they're basically sitting on top of each other, so they exert a force on one another. Okay, so there's also we have a rope as an agent interacting with both of them, so there's a tension. Okay, now technically those forces, right, A and B, like those blocks A and B, they also exert force. Let me do the internal one, right? So there's one which is friction, another one which is normal force. So they have two forces that they exert on one another. So two surface, basically there's one surface force between them, right? Like let's say this, the surface, right? One is a friction, the other one is a normal force. Then there is a tension. Well, there's also um, block A is in contact with the incline angle, right? Incline surface. There's also, like, let's say, surface that only acting on A, but not on B. Okay. And then you have entire Earth, which basically acting on both A and B. Okay, so this will be then your, interaction diagram, where my system is just two blocks, right? A and B, and they exert two forces on one another, friction and normal force. And there's a rope, tension on both of them, surface of the incline acting on A, entire Earth acting on both of them. All right. Next, we're going to do a free body diagram. So free body diagram will be then for each one, and we're going to then show which one are interacting, which one are not. Okay. So then let's look at in terms of that. Well, I'm going to first do B. So here's how I would do B. I'm going to take up as positive, like let's say up and incline, right? Because if A is going sliding down, B is going up. Okay. So let's say then this is the B, right? Block B. Now there are a lot of forces acting on it. So for example, there is gravity acting on it. So this is then F of G acting on B, gravity on Earth, on block B. There is a normal force acting on it because it's sitting on top of A. So there's normal force that A acting on B. There is the rope, right? The tension. So tension A on B. So technically, the only way, like let's say the reason it's actually sliding, A sliding, when A is sliding, the B is going up, is because of the rope. So you can say that the A acting on B through that rope, right? So A on B. There's also a friction because of the surface. So there's also F of K. And this is A on B, right? A acting on B. Right? So those are all the forces acting on block B. So 1, 2, 3, 4 forces. And it has a, there's an acceleration upward, right? And let's look at, for the A. So let me do the coordinate system. Okay. Now, one of the things I can do, I can take down technically positive because A is sliding down. So let's look at all the forces acting on, on A. So this is A basically, and this was B. All right, so let's see. Well, obviously there's gravity, Fg on A, and there is normal force that we know from the surface, right? Inclined surface is normal force surface on A. Okay. Now, but also B exerts normal force on A, which is going to be then downwards. So this is NB on A. And there's a rope in this direction. So this is rope B on A. But there's also two frictions, one with this surface, the other one with the upward surface. So that means there's two, this is, surface on A, friction, right? And this is friction that B on A. You can see, right? So the A has, 1, 2, 3, 4, 5, 6 forces acting on it. Now, which ones are action reaction? Well, action reactions are basically the ones that, let's say, they exert on one another. So for example, we can see that this normal force that A exerts on B, and then this is B exerts on A. Then there's also tension, right? Right there. A on B, B on A. There's also this friction, like that. B on A and A on B. So that means there are three interacting, let's say forces acting on them. Okay, so one through the rope, right, indirectly, but then through the friction and normal force pretty much directly. Okay, so that's basically this example over here. All right. So what we have here is interaction between Earth and any object close to the surface of Earth. So one of the things we learned that any object close to the surface has a force acting on it from Earth, which is equals to its weight, right? So, and that force was gravitational force, and we would say it's equals to its mg, right? It's in negative j hat direction. And that's basically the weight acting on this object. Well, at the same time, there's a reaction force where the object, right, let's say the ball, pulls equally hard on Earth. So let's say this is, for example, let's say 20 newtons. Then this is also 20 newtons. But imagine 20 newtons acting on a small ball and 20 newtons acting on the entire Earth. So the ball is going to be, greatly affected by this 20 newtons, where Earth basically, not even going to budge because of this 20 newtons. So very, very small effect, any effect at all. But the force is the same. So you can say force that ball exerts on Earth is equals to force that Earth exerts on the ball, which will then be mass of the ball times acceleration of the ball equal to mass of Earth and acceleration of Earth. So that's kind of what we have. But because Earth, you can see, right, this is actually plus 24. Sorry. Oh, never mind. So the mass of Earth is roughly 10 to the 24, right? So 10 to the 24. That means its acceleration is so tiny compared to acceleration of the ball. For example, roughly 2 times 10 to the negative 24 meter per second square, because the product is the same. Imagine you have a 1 kilogram object times 9.8, which is the mg, right? Then that means, for example, the force is only like, let's make it 2 kilograms, so the force is 20 newtons. That means this is 10 times 24, then times acceleration to make this also 20 newtons. That means it should be roughly 10 to the, I don't know, negative 23 or something like that as acceleration. So for that to be also 20. You can see, right, then acceleration of Earth is so tiny, so, negligible, so that we can assume that, it's not affected at all by any object around it. But for example, the sun, which is much bigger and more massive than Earth, will have, as it has a very large effect on Earth, right? Earth basically goes around, or around the center of mass of that system. All right, one of the important things about this chapter is basically look at this, type of problems where you have two objects connected by a rope, which we looked at in terms of interacting diagram or interaction diagram. But we also can use, let's say, use all of those things to actually solve for, let's say, what will be the acceleration of the system, what is the tension in the ropes and things like that. So basically solve some problems for the interacting systems. Let's talk about these two objects. You have a truck and a car, and basically a truck is, let's say it's towing the car by using that rope in a tension. Let's say, assuming that the truck is moving and it is connected to the car by a rope, and because of that, right? So let's say the rope here is, let's say, pulling the car. But one of the important things here we have is that whenever you're dealing with this, something like this, where two things, right, two objects are connected by a rope and they are accelerating, and let's say the rope here is, and let's say the rope is taut, so then acceleration of the truck and acceleration of the car will be equal to one another. That means they will be moving at the same speed at any instant of time. That's why acceleration, imagine if both of them start from rest and they start speeding up, because the truck is pretty much, connected to the car and towing the car, right? They always have the same speed at any instant. That means their accelerations are exactly the same. So acceleration of the car is same as acceleration of the truck in x direction. So we can say that the system has a horizontal acceleration ax. So this is known as acceleration constraint, okay? That means, you have two objects connected by a rope and moving together, they will always have the same acceleration. So even when those objects are kind of moving in two different dimensions, right? One is horizontal, the other one is vertical. If they are connected by a rope and moving together, right? Let's say, then still you can say that acceleration have the same magnitude. Well, now you have horizontal acceleration and negative vertical acceleration, right? If you take up as positive, then you still have kind of like, let's say, magnitude of the acceleration still equal to exactly the same, because they are connected by a single rope, and when they're moving, they move together. So then, let's say at any instant of time, if I look at their speeds, if they're started from rest, they're going to be the same, which means their acceleration is the same. All right, so this is known as the acceleration constraint, and this makes our calculation for the problems like this very easy, because you can always say there's a given that a acceleration of A and equals to acceleration of B, sort of like in terms of this magnitude. Okay. Now, here's then what we have. So imagine you have a safe that is, hanging, right, by a rope. So you can see, right, so the heavy safe hanging from a rope. So the combined pulling force of a billions of stretched molecular springs is called tension. That's what we pretty much call tension, right? So the tension pulls equally in both directions. Okay, so if you look at kind of like a small part of that, right, equally in both directions. So this small piece, right, in figure B, right, is in equilibrium, so it must be pulled equally from both, both sides. Now, one of the things we can do in this chapter, we can assume one thing, is that when we're dealing one rope, right, so you can think like this. So if you take let's say this part, okay, so imagine, let's say this point 1. So the force that, let's say acting on this rope at both direction, compared to, let's say, somewhere over here where the rope has force acting both direction, they're not technically equal to one another. Because, for example, this part of the rope, holding entire, safe and this much of the rope. Where, for example, this part of the rope only holding the safe. This part of the rope holding half of the rope and the safe. That means closer you go to the, let's say that contact point at the, on the ceiling, stronger the tension. That means tension technically increases with distance, right? Let's say that means, for example, again, if you're talking about this part, it only, equals to the weight of the rope. Weight of the safe. If I'm pointing this, then the force downward is equal to the weight of the safe plus weight of the half of the rope. The force then acting in opposite direction equals to that. So weight of the safe plus half of the weight of the rope. Okay, and if this is here, then it's weight of the rope plus weight of the safe. So it's not necessarily the same. What we do here is this then. We try to make a simple approximation, because again, if you have a system like this where you have the block A and B connected by a rope, and we apply force on block B, then that means there is a force acting on it. Then in a way you can see, right, so this force acting on B, and then, for example, then this rope over here that acting on B, right, it has to push the A, block A, plus the entire rope. So it has to be as strong as those two. Then over here, it has to push basically the, block A and half of the rope. So then the tension here is just basically has to be strong enough to pull the block A. That means tension, let's say 0.1, 2, and 3, right? They're not equals 2. So the tension 0.1 is less than tension 0.2 is less than tension 0.3. All right, which makes our life really complicated. Instead of that, what we do here, we say this. We're going to assume that mass of the string is 0, so then the string is basically is massless. Because think like this. So let's say here's your rope, right? See, if the system, if A and B are accelerating to the right, and there's a force on both sides of the rope, well, this is, let's say, tension that acting on B, tension acting on A, right? Or like, let's say 0.1 and 0.3, right? So you can see, right, if the rope is accelerating to the right, that means TB minus TA. That means this TB should be greater than TA, so there's a net force to the right, so then the rope is accelerating. Okay, which means TB not equals to TA. That means that the rope at 0.3 and 1, right, or at, the right next to the B, right next to the A, they're not equal to one another. Well, we can solve this by saying this. If TV minus TA equals mass of this, mass of the rope, let's say, times acceleration, what if we say that the rope has such a small mass that we can just set it to 0? Okay, so here, if we set this to 0, that means this is equals to 0. That means their difference equals to 0, which means TB equals to TA. So that means the rope being massless then makes all the tension everywhere on that rope to be equal to one another. That means the same rope, same tension everywhere. And that makes our life much easier. That makes our calculation much, much simpler. That means all we have to say is that if you have a rope connecting two systems, right, two objects, A and B, then you can say then whatever tension that B exerts on A is exactly the same that A exerts on B. That means tension acting on A is exactly the same as tension acting on B. Okay, so that's kind of another constraint we can make. So all a massless string does is transmit force from A to B without changing the magnitude of that force. So for problems in this book, you can assume that any strings or ropes are massless unless it explicitly states otherwise. All right.